In today's video, I'm going to show you how to control a motor with a Raspberry Pi and C++ using the pigpio library. In order to control the motors, we will be using a motor driver, specifically the L298 dual H-bridge motor drivers. I'll be using the VM Rover platform in this video so that we can see the wheels turn and we can actually see a robot moving. If you like this video and find it useful, please like, share, and subscribe. Here's the VM Rover, and you can purchase it from the website at a fairly reasonable cost. Now I have the VM1, the Rover 1. They recently did an update to the Rover 2. I don't know all the differences. It looked to me as if they were very similar, with a couple minor things, mostly in how everything was connected up. But on the Rover 1, they have a motor driver that is an L298N dual H-bridge motor driver. So one of the first questions you might have is, well, why do we need a motor driver? Can't we simply connect the motor to one of our output pins on the Raspberry Pi and simply turn it on when you want to drive the motor to get it to turn? So a couple of problems with this. One is that motors generally require more current than the output pin from Raspberry Pi or any microcontroller or embedded system can provide. And then even if you were able to do that, it wouldn't let you really control direction. So what typically happens with the motor is that you will put 5 volts at one line or one pole on the motor to get it to drive in one direction. And then when you want to change directions, you have to flip the polarity of the signals going into the motor or the current. So that's what a motor driver is for. It's to help you control that and also provide the higher current required. I found a good article about motor drivers when related to using them with the Arduino. I'll put a link to the video description to cover that. And we'll use the same approach, but we'll just simply be using a Raspberry Pi instead of an Arduino. So here is that article, and it goes through how we control a motor, why we need to use a motor driver, and how we can control the speed using a signaling type called pulse width modulation. Now, the way that the L298N H-bridge driver works is that there are 3 signals. There's an input 1, input 2, and enable. And the in1 and in2 pins are used to control the direction. We basically turn on and off certain pins to say, hey, I want to turn left, or I want you to turn in one direction, and then we swap the pins to make it turn in the other direction. And then the enable pin is where we apply our pulse width modulation signal. And that's the pin where we turn on and off periodically to control the speed at which the motor will be turning. So now that we have a basic, simplified understanding of what a motor driver does and why we need it, let's talk about how we connect the Raspberry Pi to the motor driver. So VM already has some installation instructions on how to connect everything up so that it will work with their VM software. So we followed those when we originally set up the VM Rover. And we can see here in this diagram how everything here is connected. So we have our 6 pins for the L298N dual bridge motor driver, and then these are the pins that they're connected to. Here we have a diagram layout, and here we have our list of pin connections. One important thing to note here is that these are Raspberry Pi pin numbers, not the GPIO pin numbers, right? So if you remember from one of my earlier videos, I talk about there's a difference between the number of the pin versus the number of the GPIO device. So when we look at these pin numbers and we translate them into GPIO pins or GPIO numbers, we'll get different numbers. So here I show these numbers in this README. So for the left motor, this is in1 into enable A is connected to pin 11, 13, and 15 respectively, which corresponds to GPIO 17, 22, 17, 27, and 22. And then the right motor also mapped those. Now, if we look at the Raspberry Pi hardware documentation, what we will see is that those pins don't correspond to hardware-based PWM outputs. So, like I mentioned, what we're doing is we're going to use PWM, pulse width modulation, on the enable lines, so NA and NB, which is GPIO pin 22 and GPIO pin 25. We look at the Raspberry Pi documentation, and GPIO 22 is simply just a regular GPIO pin, and the same thing with GPIO 25. Whereas some other pins, like GPIO 12 and GPIO 13, have this PWM 0 and PWM 1 next to them in parentheses. So these two pins are hardware-based PWM pins. So it means you can generate PWM signals on them in actual hardware, versus if you wanted to get a PWM signal on any of the other GPIO lines, you have to do that manually by turning on and off the pin, the output pin, by simply writing some code to turn the pin output high and low, similar to what we do using the same structure as the LED, but instead of just turning it on, you need to turn it on and off at a rate to get the PWM signal. So the VM Rover base connections don't use hardware-based PWM and use software-based ones, so we need to make sure we're doing the same. Now, I could go and change the connection so that we are using hardware-based PWM pins, but for now, I'm not going to do that. By sticking with the same connections that VM recommends or provides in their installation instructions, it lets me easily switch between using VM and my own built-in application. So this is a nice way to verify that what I'm doing works, and that if my code doesn't work, I can switch to VM's software and be like, okay, well, it is working, so what am I doing wrong? Okay, so let's look at the software and see how we actually do this work using pygpio. So here we have the first application where we will be using pygpio methods directly. We include pygpio header, and then we specify the pins we're using. So for this example, I'm just going to be looking or controlling the left motor, and the left motor is controlled by GPIO 17, 27, and 22. So we set those up, and then we enable the pygpio library, initialize it here. We disable the signal handler like I talk about in another video, and we've set up our own so that we can shut the application down cleanly. Then we configure all of the pins. So I need to configure all of these pins as output so that we can control both the direction and the speed of the motor. And then I simply write to the pins. So in order for this to work, we need to set in 1 to high and in 2 to low. So the direction is going to be controlled by in 1 being high, in 2 being low, or in 1 being low and in 2 being high. So in 1 and in 2 need to be opposite to each other in order for the motor driver to work. If we go back and look at this article about motor drivers and H bridges, we'll see why. So if we are controlling the direction by toggling these switches here, then one needs to be open while the other is closed. If they're all closed, then current will not flow through the motor. And if they're all open, then no current will flow through the motor. So what we are doing is we are changing the direction of current flow through the motor by controlling the in1 and in2 pins. So in one direction, the motor will turn clockwise, and in the other direction, the motor will turn counterclockwise. So they must be opposite values. And then we control the PWM output using the built-in pigpio PWM function. So this function is actually a software-based PWM, and it can be applied to any GPIO pin. If we go look at the pigpio documentation, we'll see that it supports both hardware timed. It's hardware timed, but it's PWM on any of the GPIO lines. But it also supports the built-in PWM pins. Do a quick search of PWM in their documentation, and we see that there's a wide variety of functions here. So this is PWM commands. It's the generic one for on a GPIO line, but they also have a hardware GPIO or hardware PWM that is for controlling the PWM on those specific pins. So because the motor driver is connected to just regular GPIO pins, we will be using the GPIO PWM function. And that's what we do here. Now, the way this function works is that it takes a pin that's going to be controlled and a duty cycle. And the duty cycle is dependent on a range. I didn't play with range too much, but basically it's going to impact your resolution. So the default range is 255 values, but you can change the range to different sets. And what that will do is give you different resolution. Depending on each individual integer value you provide, it'll be a slightly different PWM length. I just stick with the default, which is 255 values. So if we think about PWM in terms of high time, like how long it's high, do you want it high 100% of the time? Do you want it high 0% of the time? Do you want it high 50% of the time? Then we need to calculate the correct integer value out of our range to achieve that percent time high. Right here we have a little example. So if I want the motor to constantly spin at the max speed, then I set the value to 255. If I wanted to spin at half speed, I would set it to 28. And if I want it off completely, I would set the value to 0. So in our code, we're going to say, hey, I want it to be high 50% of the time. So our duty cycle value is 128 because it's half of 255. And then we simply say, turn on the GPIO PWM. We start that using this function. We verify that the function worked as we expected it to. And then we simply wait forever in 100 millisecond increments. We have this sleep of 100 milliseconds here so that we can detect when the application is stopped manually. And then we stop the output, the motor, by setting the PWM to 0. So if you don't do this, then there is the possibility that your motor will continue running. Because remember, what's happening here is we are turning on and off the motor. So we're saying go, don't go, don't go, go, at a rate of 50%. So depending on when we terminate the application, the motor may be running, in which case the application ends and it never gets told to turn off. So now the motor just continuing to run. You'll see this very clearly if you were to set this to just always on. then when you shut down this application, if you didn't have this, then the motor will just continue running. But because it is a duty cycle, I ran into this problem is that sometimes it will shut down and sometimes it won't, just depending on when the application shuts down and where in the duty cycle the PWM output is at. If you don't do this, then your robot potentially can crash into a wall or fall off a table or get itself into a situation where it gets damaged because you forget to turn off the motors themselves. Let's run the motor control application and let's see what happens. So we can see that the motor is turning, and that green sticker with the black arrow is meant to highlight the direction of the turn. So we can see that the motor is turning in a counterclockwise direction. If you want to make it turn in a clockwise direction, then we need to change which of the in one and in two pins are set high. So to change direction, we set in one to be low and in two to be high. We make that change and we remake. And now when we run it, we'll see that it turns in a clockwise direction. I also can control speed by changing the duty cycle. So currently we have it set at a 50% duty cycle. So it's on half the time and off half the time. If I set this to be a closer to 100%, let's say 240, then we can see that the motor spins more quickly. In the last video where I talked about controlling a switch, I introduced this libgpio wrapper library that I wrote in order to simplify the interface into the pigpio library. And this structure actually will give me a lot of long-term benefits. I can easily swap out the underlying GPIO control library with one of the other options, and my code won't be impacted by it as long as the C++ classes I've created stay the same. So it gives you a lot more flexibility when you write your code versus calling into some specific library directly. So I highly recommend that you attempt to design your software this way because there's numerous benefits to it. So keeping in that vein of wanting to simplify the way we interface with the code, I added a motor driver class. So this motor driver class is what I will be using going forward to control an individual motor. You can see that the constructor for the motor driver class takes in the 3 pins that I need in order to control both direction and speed. And then it provides some functions to do that. So I can set the direction as either forward or backward, or set the effort. Now, effort is a term that's used pretty commonly in my day job to mean a percentage of the maximum that's allowed. So what you're actually controlling isn't known or doesn't matter. We just need a percentage of that. So for example, in a PWM, effort would be the length of the PWM signal. So I want 100% effort means 100% PWM length. 0% effort means 0% or whatever the lowest value of your PWM signal needs to be. And 50% would be halfway between. One way I like to think about it is when you're driving your car, if I were to press the gas pedal all the way down to the floor, that's 100% effort. If I take my foot off the gas pedal, that's 0% effort. And then there's a range in between. So that is just how much percentage you want to apply to whatever physical system, but that doesn't translate directly into speed or velocity or anything, or acceleration or anything like that. So just how much effort are you willing to put into, are you wanting to achieve this goal? And in this example specifically, effort talks about PWM. We could have used a term like PWM length, 50%, 0%, etc. Effort is just a more generic term that is, again, commonly used in most of the robots that I work with. Another thing that I did since the last video is I refactored a little bit of this libgpio code, I introduced the idea of a generic digital output device from which an LED is a type of digital output. I could have used the LED class here to control in one and in two, but that felt really strange to say, well, a motor driver consists of two LEDs and a PWM. No, they consist of two digital output signals and a PWM signal. So we refactored that code so that when we think about a motor driver, it makes more sense from a holistic view, right? I'm controlling two digital outputs in one and in two, and then there's a PWM output. In this iteration of the motor driver code, I use the digital output class to control or set in one and in two, but then I'm going to use the pigpio function directly to control the PWM. In an updated version of this library, we'll probably also encapsulate the PWM function inside of a class. But for now, for simplicity, this is what we're doing. So what that lets me do is I can instantiate the two digital output devices, input pin 1, input pin 2, and then I store off the GPIO number for the enable pin. And when I want to change directions, I simply say, hey, pin 1 set output true, pin 2 set output false, or vice versa. So again, this simplifies the code I have to write at the motor driver level. And the actual functionality, the calls into pigpio, would be inside of this digital output class. So here's what I call GPIO write. When I want to set the effort, I'm going to call GPIO PWM function directly. And you'll also notice that I'm taking a double value. So 0%, 100%, 50%. And then we translate that into an integer value because pigpio is expecting an integer value based on the range. So 50% would be 128, and 0% would be 0, 100% would be 255. So we scale this to an integer value. We then can set the GPIO PWM duty cycle we would like, and then we check to make sure that everything worked correctly. So again, this is going to look very similar to what we've done before with the digital output or LED and the switch functionality where we execute the pigpio function and then we check to make sure everything is good. And if it's not, we can throw a runtime exception that we can catch and potentially try to handle. So using the libgpio classes library wrapper, this is what the code looks like. So we still specify the pins that we're going to be using, and then we instantiate a motor driver. I can say this is the left motor, and then I can say set the direction to be forward, set the effort that we want to apply as 50%, and then stop, do that for 2 seconds, stop, switch directions, and go backwards or the other direction for 2 seconds, and then stop, and then repeat that indefinitely. So if you run this code, we will see that that does happen. It runs forward, which in this case is counterclockwise, then it stops, then it runs backwards, which is clockwise, then stops and repeats that. So now we are able to simplify our code quite significantly, and we're able to think about the movement of the motor in simple terms of direction and effort. And how that's implemented in terms of an in2, in1 digital I/O pins and a PWM signal no longer matters. So when the hardware changes later, or if the hardware changes later, or the motor driver we're interfacing with changes later, this code doesn't have to change. We would simply change what's happening behind the motor driver or inside of the motor driver class. And I can think about my code in pure terms of I have a left motor and a right motor. Now you might say, well, that's great, but forward is kind of weird. Like maybe you don't agree with my direction for forward, and that you think forward should be clockwise and backwards should be counterclockwise. That's an easy thing to solve by simply switching which pin is in one and which pin is in two. So if we swap the in one and in two pins from pin 17 and 27 to 27 and 17, then now forward will be clockwise and backwards will be counterclockwise. So moving forward, we're moving spinning clockwise. We're moving backwards, we're moving counterclockwise. But remember that these directions are arbitrarily selected by me in this situation, and the context matters, the frame of reference matters. So, yes, the wheel is turning clockwise, and maybe to you that means forward, but what does that mean from the perspective of the robot? So, in Motor Controller 4, we actually are going to control both motors. We're going to set them both up, instantiate left motor using in one, in two, and enable A, and then right motor using pin 3, pin 4, or in 3, in 4, and enable B. And we're just going to have them turn in the same direction at the same rate. So what should happen is that the robot should move forward smoothly in a straight line and then move backwards in a straight line. Now, which of these is forward or backwards, we'll see in a second. So we're going to move forward, we're going to stop, we're going to move backwards, we're going to stop, and then we're just going to repeat that indefinitely. So if I run Motor Controller 4, what we will see is that the left motor, right, is as we've seen before, forward is counterclockwise, backwards is clockwise. And then for the right side, backwards is counterclockwise, forward is clockwise, which is the opposite to the other side. So the left side and right side spin or appear to spin in opposite directions when you're looking directly at the wheel. So although the forward and backward are different in terms of the direction that the motor spins, we'll see now that setting forward and backward, actually the robot moves in the direction that you expect it to. So when I run this, you see forward, the robot's moving forward, and then when it goes to backwards, the robot moves backwards. So again, just highlighting that the frame of reference really matters. What is the thing you're talking about? What is the perspective that you are looking at it from in order to determine what means forward and what means backward? That's it for now. Talk to you soon. Later.